This is Asynchronous Python, a gentle introduction. You have all won the survey, so to speak, and you get to spend the next 30 minutes or so doing this. I do hope that I can make it entertaining and appealing. This topic is full of misconceptions. The way that it's spoken about, even the way that it exists in some of the documentation, is deceptive. Which is why I chose this image to set the tone. So the way that we talk about asynchronous programming or asynchrony or async.io or any of this, we talk about it as if we're doing multiple things at once. And yet, interestingly, so what is the term for this in our culture? Well, we call this synchronized swimming. So already we see that the language is working against us to understand what asynchronous programming is. Like, you would think that would be it, but we call that synchronous. It's a starting point. So here I'm going to define it and disambiguate related but independent concepts. Then talk about coroutines. You'll see why, I'm just picking a small number of very important topics, and that is as such. We'll do a very brief survey of some implementations, but what I like to teach you is largely implementation independent, and ideally is evergreen material. If the material were no longer useful next week, well, then that would be bad in the long term. So. Yes, and first steps toward asynchrony for program and some async IO tips. You will see that I have a preference for that. I am targeting only CPython 3.7 here to make this, once again, last long and be useful. And I decided to modify the talk proposal. I'm no longer comparing implementations of a program, a realistic program, using different libraries. But I can talk to people about that afterwards. I'll be around, so I don't want it to be too much of a bait and switch here. Consider this information available to whoever wants it. Given that this is abstract information, let's do this Socratically. Don't hold questions until the end, and I will feel very comfortable with no malice to choose to say off topic, or we'll discuss it later. And we'll just go that route, or we'll discuss it now. Okay. So this is really this is syntax low. I think that a gentle introduction to asynchrony being here's an await syntax from async.io is an anti-pattern. It's really not enlightening. We are going to take an opposite approach here. So. Okay, we're going to start talking about processes and threads. Threads have shared memory, processes don't. Processes don't share memory space between each other. So multi-threaded applications, or even multi-process applications, the problem, most of the difficulty comes down to synchronization, which means even if they're doing different things, and at the same time, even if they're doing different things, we eventually need them to communicate at the end some useful information to each other, obviously. And then there's a whole subset of information you can look at for inter-process communication. It is going to be highly relevant to whatever work that you're considering using asynchronous programming for. Yes. Okay, so more confusing terms being cleared up for us all. These are all these terms thrown around. So we have this idea of concurrency versus parallelism. They are not the same thing. I happen to believe that I really like the definition on Wikipedia, so I cited it. Don't tell anyone. But I provide that full disclosure in maybe, get a second source if you need it. This is not supposed to be considered canonical. So they are different. So basically, parallel computing, you're doing two different things at once. Concurrent computing, you're able to do two things. You're only able to do one thing at a time, let's say, but you can divide your time evenly. We like to think of ourselves as multitaskers, And we're not really. Like sometimes if we want to do A and B simultaneously, we really switch from A to B to A to B to A. And we pick up where we left off with each. Another prerequisite topic here to talk about, preemptive versus cooperative multitasking. Technical difficulties. With cooperative multitasking, your code will volunteer to give up control often in the case of asynchronous libraries, some event loop or something, but the code is deciding that it wants to give up control. Now, this caused notorious problems in like Windows 3.1, because if someone makes a program that takes all of the that doesn't give up control, then it's bad for everybody else. I mean, this would be probably a poor way to structure an operating system. But in this case, if you and your team are responsible for all of the code, then you can make sure that everyone plays nicely. No one will try and hog resources from anyone else. Preemptive multitasking, the opposite. This is the idea that the operating system yanks control away. So as annoying as it is with cooperative multitasking to consider other threads when writing the current thread, it's actually easier than preemptive multitasking, because the code doesn't need to be prepared for some external force to steal it away without notice. All right, and blocking versus non-blocking. So the idea of, and we generally talk about this in terms of I/O because it's slow, but it's not I/O specific. So there is, if I'm using steps 1, 2, and 3 to perform some task, and step 3 waits for step 2, well, if maybe it needs to wait for step 2, maybe it does not. Obviously, it's a function of whether or not step 3 uses the output from step 2. If step 2 in our program prevents step 3 from happening until it's finished, then we consider it blocking. So in practice, let's say that action 2 is really going to town and doing some hardcore processing. Well then, and this is part of the hype problem here. If that's the case, then it wouldn't be useless for us to try and make this somehow non-blocking, because it would be occupying the computer, be occupying the processor. So the key idea here is, while I'm waiting, if I'm waiting on something, can I do something else? If the computer's already using its resources, then there is no benefit there. So asynchrony, the technical definition's a bit broader, but it's generally like, we can think about it as a style or a paradigm, where we're doing a single-threaded programming. So one thread in one process with a queue of non-blocking tasks. So we set up a queue. The queue, we execute the tasks on the queue. Things are often being added to the queue. They're being removed from the queue. You can think about this within the context of an event loop, which we'll get to in more detail later. But this is one thing at a time. I give this example of baking bread while doing dishes. So I have two hands. I need the hands to perform baking tasks or to perform dishwashing. I personally would be very impressed if you were able to wash a dish with one hand and bake bread with the other. Let's assume that's impossible. But please prove me wrong. So in this case, I can do one or the other, one thing at a time, but my state is retained when I return to my previous context. So if I go back to the dishes are where I left off. So it's not as if it's not as if I do a task to completion, then do another task to completion, then do another task to completion. The key here is that none of these tasks they're all stopped before they're completed, and then we go use them again. So it's commonly stated, go asynchronous, it's fast. Well, is there speed boost from this? Well, if we're going to make things easy and just compare single-threaded programs to other single-threaded programs, well, the theoretical maximum gain that we can get from this is that we never have an idle thread. So, I mean, it's not massive. I mean, we're not talking orders of magnitude here. But okay, we could be talking orders of magnitude. I take that back. It really just depends it's a function of how much the thread is waiting. Now, in a lot of circumstances that people care about, like a web server, there's a lot of waiting. There's a lot of latency issues, connectivity issues. Other times, I mean, if you're doing like some kind of local heavy number crunching operation on your laptop, I mean, if you're pulling from even your hard drive, much less external sources, there might be a lot of I/O that could block. On the other hand, if you are just doing lots and lots of calculation or computation, perhaps not. Just we look at this from the in case and the out case in order to more fully understand the in case. It can be useful to think about what asynchrony is not or what it cannot do. So, I want to thank Robert Smallsher here. I'm using some of his slides because he's a little more visually inclined than I am. So check out 60 North, particularly if you are based in the United Kingdom. So here we have some visual representations of what I'm talking about. So let's consider the orange and the red lines as, we'll talk about them as threads, or generally like each one is doing something. So we can see here concurrency versus parallel. So we're not starting over every time we do the concurrency, but we can really only do one thing at a time. However, as we said, if there's waiting around, then that can be much more efficient. So here we can see asynchronous. We don't wait before we proceed. We can start a task, and then if the control is released by that task, remember our cooperative multitasking, then we can move on to the next thing and go back and look. And then, of course, we compare this to sequential. It often takes more time. Here's preemptive multitasking. Here's cooperative multitasking. Tasks yield to scheduler. A lot of terms are used similarly. We should think about the event loop, as it's so often called, as a type of scheduler. So we'll think about an event loop as a type of scheduler, and I like to think about an event loop. It's got the loopiness. Yes, it's true, but like maybe it'd be useful to think about it as like a queue of tasks. I think it's useful to think about it as a queue of tasks as well as a loop, because the stereotypical situation is one in which we are just letting an event loop run and it just runs forever. But there are other common use cases for async IO and other libraries where we have we create a queue of these tasks, and then we run them. And then we relinquish control flow back to some other more classical, more Pythonic style of programming. So yeah, so the queue is even more omnipresent than the event loop, as it will. And the event loop we can think about as a type of scheduler. So let's look at the coroutines now. So, because this is like the other big key concept here. This guy, Donald Knuth, you are probably familiar with. So he talks about, so subroutines, as we know them, functions, you think about them as a subset of coroutines, a less powerful version of coroutines. Generators, also called semi-coroutines, are between the two. I mention this so that you can take your previous knowledge and apply something alongside it, rather than create some new concept. It would be a waste. So when we think about a function or a subroutine, we go in and we go out. We've got an entry point, we call it, and then it returns a result. So coroutines can do that, but they allow multiple entry points and re-entry points for suspending and resuming execution for non-preemptive multitasking. So basically, they're like the foundation on which you, as a new asynchronous programmer, are going to rely on. You're not going to be creating event loops. You're not going to be writing libraries, writing frameworks. Like you'll be, if you want to program asynchronously using a framework, you're going to be using coroutines, which is why they're important. Now you can see they're called tasklets, generators, async await versus generator syntax. you know, these greenlets, they have different names. They have different syntaxes. Async await and generator syntax are both like C Python standard syntax. But you know, we're trying to look at this just a hair more abstract than that, and they're the same thing. Now, of course, there's just more broadly there are generators that you know you're familiar with, and as you recall, they are kind of in between. If we think about a generator, like a generator does have it's a less powerful version of a coroutine, so that makes total sense. So we initialize the generator, and then we give it some input when we start it, and we have and then we can send it additional information, and we can call next on it. So we're suspending and resuming. The other really important thing to know here is, so a coroutine is code plus state. So when we see, I think I have, so like here's code for writing an asynchronous coroutine. So we call this a coroutine function. And then when we call it, we get something back. We get an object back. That is the coroutine. That is the coroutine. All right. Yeah, so these are the things a coroutine can do. You can await a future results, yield from same thing, different syntax. So you can await a future or a coroutine. Future, I wish I had more time to get into a future. We could just think about it as a placeholder for where a future value will be. Which it takes a few minutes to wrap one's head around. So don't worry if you don't get it immediately. It took me a while. And you know, of course, we can return and raise. An important digression here is this exception handling is very nice. Let's think about the way we might intuitively, from the ground up, handle something like asynchrony. We might call a subprocess, for example. There's not a lot of control. The fact that we can bubble exceptions around in these things, even though they don't follow a stack or a tree in terms of function calls, because they're coroutines and they're too cool for that. We can still have exceptions float around, and that is very helpful. So anyway, yeah, you know, I won't get hung up on it, but you provide it with an iterable and a predicate when you initialize it into a coroutine, and then I mean, if you wanted to call this, I believe you could use send on it. You could send is like next, but you can add a parameter to it. This looks like it's more of a standard like generator style thing. Hey, question. Yeah, what's the predicate? So in this case, predicate is just an abstract way of saying like this, like you pass it a function. Like if you can see on line 3, you're passing it a function that it will operate on for the item. So it's just like if you can think about like if you're doing a more functional style of programming, maybe you might, if you want to do something to some strings, you might pass the function capitalize, and then inside of another function, you pass the capitalize function, and then you call it within. So it would be, yeah. So that's what's going on there. Can you explain like what part of this makes it a coroutine? Yeah, he wanted to know what part of this makes it a coroutine. A really good hint that you're dealing with a generator or coroutine is the yield. And in this case, this would mean that the control flow is voluntarily given up. So yeah, generally if you see a yield, you're definitely dealing with a generator or a coroutine. No, yes, another question. Yeah, this is pretty similar to a generator. This would probably be a better example if yields was waiting on a future value, for example, like using await or using yield from. Yeah, I probably should have used the different coroutine function. But yeah. And obviously one function, any given coroutine or subroutine within itself, there are no clear benefits of asynchrony there. We need to see how this would play with other functions. With other coroutines in order to like really understand the benefit. Yeah, because if you just have a single coroutine, it's basically as useful as a single subroutine. So we'll talk about event loops. So let's think. So we've got this concurrent style where we can sort of put things on pause and resume them, and this can be very useful, if we think about like these. So if we think about like an event loop, this is where we're adding things to, we're constantly adding tasks to this queue, and we're constantly executing them. Basically, like for async IO speak, we make a coroutine into a future. So we're just like kind of thinking about like what's the next value that the coroutine is going to yield. We'll make that into a task. And this is once again, it goes back to the shared state. Like if I have a coroutine, if I have one coroutine function, there could be 10 coroutines of it, because remember, we call that and then we add state, and maybe each one of these is some certain amount of the way through, because we can volunteer away execution control, cooperative multitasking again, and then get it back. So they're kind of all over the place. And there is, if you really have to use something that's blocking or something long running, you can use an executor. There are two different types of executors that are in the Python standard library. It's just kind of like an easy way to spin something up to do a task that maybe you don't want in your event loop. This should be first. Here's an event loop. We've got like eight slots, let's say. We put something in a slot. We're kind of, imagine us spinning around this, and this is kind of like the dumbest possible event loop. So we've got this task queue, 1 through 8 are tasks. This one is smarter, and this is actually the one that async IO uses. So instead of just blindly running around and checking like, hey, does this task need anything? Does this task need anything? Here it knows to look a bit smarter. It's got, I guess, a higher hit rate. So let's talk about why this is difficult. The feedback and the failures are subtler. I think that we can often be spoiled if we're doing software engineering, because we get such wonderful feedback of a failure. Worst case scenario, we complain that there's a non-descriptive error message. But imagine most fields. Most fields would kill for just free validation in like half a second. In this case, you can be in a situation where perhaps the code is, say, running, like there's a blocking function call. You run it, it looks the same. You can try timing these things, and then but then you're getting into like empirical or statistical ways of validating. It's messier. So that's tough. And then the other thing is, the very nature of like voluntarily giving up control, you're worrying about what other threads are doing. You're worrying about things that are going on outside of the same like code space as wherever you happen to be in your text editor or what have you. You have to think about things that are going on outside of that. So it's similar to thinking in a different abstraction level simultaneously, which of course people do with low-level languages, whatever. But yeah, you have to be concerned about that. And that I think probably requires some new synapses to be built. So some first steps toward asynchronous. So we talk about here scaling here, maybe processes, we get tens, of simultaneous paths of execution. Threads, hundreds. Async, we're talking thousands here. Now, of course, that's because, a single thread, threads are a little heavier, they take more RAM, processes even more so. So, once again, you're not getting thousands of times speed boost in like the theoretical sense, but practically, if you have, say, a web server and there are 500 people all using typical like cell phone data plans or something, then in practice, you're going to be able to handle all of those connections, because they're all just going to use the same. They're just going to use the same event loop, the same thread, what have you. So they're light. they're light, but with the caveats that I gave earlier. So first steps toward asynchrony, ask if there's a package to do this thing. There often is. AIO-libs is a wonderful collection of packages. They curate them. I mean, just, practically speaking, it's nice to have something practical in this discussion, right? So, like, check if you need to, what you need to do asynchronously, or what you're considering doing asynchronously, there's probably, like, the database calls, HTTP requests, whatever, like, those are available, that's around. Whether or not you have this, I think that the async IO is going to be, the best bet, if you're talking 3.7 and onward, Greenfield project. It's a ton of documentation. It encompasses both high and low abstraction APIs. I mean, we don't even have time here, obviously, to get into like protocols or transports or like a lot of the I mean, people, you can use async IO to build something that's high level. Like it's got like, you can think about this await async syntax that people love so much as like a real tip of the iceberg. I mean, it's just massive. So, and there's some history here as well. So, stackless Python is probably the oldest thing on here. It allows taskless, which are like these like coroutine futures. It's like it patches C Python, I think. Don't quote me on it. And then, so Greenlit is a spin-off of stackless. It's just good to know how these things are related. Greenlets and eventlet and eventlet and gevent use greenlets. Whatever, gevent is inspired by greenlet. You can tell there's a lot of incest here. There really aren't that many like projects that are like doing the core asynchrony when it comes down to it. And then here's Curio and Trio, which it's useful for you to know about. They're new kids on the block. More very practical stuff. Use Python async IO debug. When you are running code locally, it will help you a ton. It will give you warnings and errors that will otherwise not be there, and they're helpful, and they handle like this crazy new style of thinking where you have to worry about other threads when you're worrying about other tasks when you're worrying about your own task. Another thing to consider is releasing the task once in a while via something like async IO.sleep, and you just sleep 0, and that says, hey, I'll volunteer to give up the task. But that's sometimes less important. If you want to know when that's less important, then talk to me afterwards. The blocking library functions, these are incompatible. You won't necessarily get an error, but these are blocking, so you will not receive benefits. You will not receive benefits of asynchronous because they'll block. Further reading, please refer to the work cited. There's this guy, and there's this guy. Extra thanks to Robert Smolsher and to Sebastian. Sebastian Matot over here, as well as, of course, everybody else. So you should also know that I am seeking pan-industry Python contractor work and a job in finance. Do you have anything for me? Let's do some Q's and some A's. We got a few minutes, and I would love to be able to get some questions. Do we have any? Okay, this fellow.
Hi. Can you give an example? So we're all at PyData, so I was just wondering
Yes.
if you could give us an example of a data analytics workflow that can take advantage of asynchronous.
He wants an example of a PyData friendly example. Okay, if you need to make a calculation for which a prerequisite for the calculation is doing thousands of HTTP requests, then you will be able to do them. You will be able to do those requests, those API calls, much, much, much faster if you go the asynchronous route. Do we have a question in the back?
So all these coroutines that are executing, these are being scheduled, are they all on the same CPU?
Are all of the coroutines on the same CPU? I will one-up you. They are on the same CPU, on the same thread. And I think that's probably what people don't understand. And that's why, there are not really two things being done at once. It is not parallel. Asynchrony is not parallel. You're doing one thing at a time, executors aside. Question in the front.
So if you're using threading, Python itself is choosing when to switch context based on CPU state, right? But the burden is on you if you're using async to decide when to switch context. Is that correct?
So the question was, is the burden completely on the developer to decide when to switch context asynchronously versus if someone's doing something more Pythonically, is it decided for you? It's nuanced. I would be happy to talk to you about it afterwards. I promise I would talk to you about that.
If you were threading all the list of blocking libs would behave more friendly if you were threading, right, versus async.
Multi-threading.
Yeah.
Yeah, I mean, if you're multi-threading, then then you can do things in a parallel fashion. But I will address. Do we have any other questions? Are we good on time? Are we good? Okay. So I saw one over here, maybe. All right, this fellow.
You mentioned Python 3.7, which isn't released yet. So
Yeah.
what are the new features related to async in Python 3.7?
So I specifically only looked at the documentation for 3.7. I know that the async and await keywords are pretty new. I think they're 3.5 or 3.6. I mean, I didn't go out of my way to make it backwards incompatible. When possible, it's good that it is. I did not want to consider 3.6 and before, but pretty much everything I'm saying is if you have 3.6 at home, pretty much everything I'm saying will be completely accurate. Okay. Wait, we got a question?
So how does await work? Is there some sort of an implicit promise in the future that's being considered?
So he said, he asked, how does await work? So await is a nicer, more async IO way of writing a yield from. And yield from is just where we relinquish control to another future or coroutine, and whenever that future or coroutine pops up with an answer, then we go back to the parent coroutine with that result.
But we don't have direct access to the future.
I mean, it's a. Yeah. I mean, it's, right. You don't for practical purposes. No, you don't have direct access to the future, but you do have access to its result whenever you're lucky enough for it to arrive. Okay, so we are finished. I do thank you very much. Please look around for me, ask me questions, talk to me. Thank you very much for attending. I do appreciate it.